All right, the order of the day is properties of groups. If you take a look in your book, what you will notice is that what I'm about to present to you goes way beyond what the book actually says. Um, what I want you to understand about this presentation is that there are some trends in here, and these are trends that you need to be aware of. In some cases, you're going to know some of the stuff already. But what I would suggest is, watch the video, but definitely print out this PowerPoint presentation to have it as reference, because there are certain things within it that can be really helpful here and there. So, overwhelmingly, though, there's a little bit of memorization involved, but honestly, don't go crazy here. It's really about understanding more of a trend than anything. So, anyway, properties of groups. Oh, that looks pretty. I don't even know what's going on there. Anyway, what we're going to see is we're actually going to take a look at each of the individual groups of the S and the P block and talk about some characteristics that they have. But before we get started, I want to talk to you about something called metallic character. So this is sort of another like periodic trend. So if you take a look at the periodic table that I have on this slide, you'll see that I have a line going down, increasing from top to bottom, meaning the most metallic would be the bottom left corner, and then the least metallic is in the upper right corner. Well, heck, that should make some sense, right? All the metals are in the left, and then the upper right corner is the non-metals, so again, that's not really anything that you don't know, but maybe we just haven't said it as, by the way, metallic character. So increasing metallic character as you go down a group or from left to right across the periodic table. So basically what we have, the reasons for the changes in metallic to non-metallic character are attributed to what we've already talked about, ionization energy. Low ionization energy elements have more metallic character. They tend to be more metallic, and that should make sense. They're cations. They want to they want to lose electrons, and that makes them metals. All metals are positive. I mean, a lot of this stuff, it really kind of connects to things you've learned before. High ionization energy elements, those are the ones that they want to become anions instead of cations, and they tend to be nonmetallic, and then they're in the upper right corner. Excuse me. So type of oxide, and I'm going to talk about oxides a little on the next page also. But there are three types of oxides, and all that means is that an element combines with oxygen and it forms a compound called an oxide. So your type of oxide will also indicate metallic character. And in parentheses there, I have three different types of oxides. You can have an oxide that's acidic. You can have an oxide that is basic, and I think we probably understand what those mean. But then the word in the middle, amphoteric, basically means that it has both acidic and basic character all at the same time. For those of you that were in my class, and I'm not sure if Mr. Wolf covers it or not, but when we talked about acids and bases, I mentioned that water is amphoteric, that it actually can act as an acid and a base, and that's what it means. So a chemical, one of these oxide chemicals that would be amphoteric, it just has the ability to act both as acids and bases. For the acidic oxides, you're going to have the least metallic character. And then for basic oxides, it's going to have the highest metallic character. So if you take a look at the trend line, least to highest, the least metallic character, imagine like right up over here. So these are going to be the least metallic, and they would have acidic oxides, and then basic oxides would be at the bottom. So just to be clear about oxides, knowing the trend, not worrying about memorizing everything's, whether it's acidic, basic, or whatever. But what you'll understand is that basically from top to bottom in a group, that you would go from acidic to amphoteric to basic. And that is going to be indicative of, it's one of my favorite words, metallic character. So, for example, if you would look at group 4A, which has carbon at the top and lead at the bottom, you actually, as you go down the elements, you have a nonmetal, right, carbon. You have a metalloid, silicon. You have another metalloid, germanium. And then you have two metals. You have tin and lead. So at the top, your carbon is going to be an acidic oxide, and then your metalloids, your silicon and your germanium, those would be amphoteric oxides, and then you end up with basic oxides at the bottom. And so this is just, again, a general trend that if you are a nonmetal, you generally form acidic oxides. If you're a metalloid, you form amphoteric oxides, and if you're a metal, you form basic oxides. So if you take the same principle and apply it to, for instance, group 2A, they're all metals. So if they're all metals, they're all going to be basic oxides. If you apply the same principle to 7A, fluorine, chlorine, bromine, iodide, those are all non-metals, which means they all have acidic oxides. So it's, again, just a trend to try to understand, and if you want to think it goes in alphabetical order, A at the top, B at the bottom. So to just do a quick run through with each of these groups, and what I'm going to do is pretty much just put everything up on the screen, and then I'll kind of talk through it little by little. Hydrogen is special, so hydrogen is going to get its own slide here. Different properties than the other 1A elements, so it is in a group completely by itself. It's colorless, it's diatomic. It has the ability to form either a +1 or a -1 ion because it only has one electron, so it's sort of like, I could either get another one or I could give it away, I don't really care. And we should know that H plus is present in anything that would be considered an acid, and I have two examples for you here, hydrochloric and sulfuric. And then if you see a chemical like this, that chemical is called a hydride. So this would be the negative form or the anion form of hydrogen, and that would be called lithium hydride. So just some special things about hydrogen. To go with the rest of the group 1A metals, these are called alkali metals. To be clear here, N is energy level. So you have, you could say it's a 1, S1, but really what you're looking at is the S1 portion, that you have one electron in your S orbital, one valence electron, and that's your alkali metals. So they have an ionic charge of +1 because of that electron configuration. Their oxides tend to form this formula, which makes sense because oxygen is a -2 and they would be +1, so they form basic oxides. Basic oxides because the atoms are metallic. The halogens, when they combine with a halogen, will form MX, like for instance NaCl. So Na is an alkali metal and a halogen is a Cl, so it's a 1-to-1 type of ratio with their charges. These metals tend to be very soft. You can actually cut them with a knife, which is kind of cool to think that it's a metal, like a big chunk of metal, and you cut it with a knife. And the reactivity will go down as you go down the periodic table. So for those of you who are in Mr. Wolf's class, I know he does a demonstration where he will react lithium and sodium and kind of compare those. So lithium does have a reaction with water. But sodium has a little bit more of a violent reaction with water. And if you keep going down, potassium, when you even put the tiniest little bit in water, it catches fire, which is pretty cool. I don't believe we have any solid potassium here in school, so that's probably a good thing. But speaking of the reaction with water, when they react with water, they produce hydrogen gas and a base. So if this is the reaction, as I just explained, let's say we're going to react lithium with water, I'm supposed to produce hydrogen gas and a base. My question for you is, what base? Let's see if you got it right. Would that be a base? LiOH? Yep. Anything with OH is a base. This is an equation that it's a good idea to have a handle on, to understand that when alkali metals react with water, that this is what's produced. Essentially, it's a single displacement reaction. If you rewrite H2O as HOH, you have a lithium go with an OH, and then you have your hydrogen left over, and it's a Hunkelbreff or a diatomic, so it has to be H2. So that's a good one to keep in mind. Your group 2, they're called your alkaline earth metals. Electron configuration is S2, so whatever energy level, S2, so 2 valence electrons, which means they have an ionic charge of +2. They are also metals, so they form basic oxides, and their oxide will have a formula of MO because the oxide would be -2. The ionic charge of the alkali earth metals is +2, so they cancel out. If they blend in with a halogen, if they combine with a halogen, it would be MX2. So for instance, MgCl2 would be a formula of the halogen version. They are chemically reactive, but way less reactive than the 1A elements. In fact, you could take a strip of magnesium and put it in water and it doesn't react. Like sodium, its next door neighbor would. But if you burn magnesium, yeah, it's energetic. Very, very bright. In fact, the bright white flares that they have in the military are actually magnesium flares, incredibly bright, like they light up the sky like it's daytime. But the reactivity, similarly to the alkali metals, does increase as you go down a group. And that's that, group 2A. So group 3A, again, you can see a change in the electron configuration. So we now have a full S energy level and now a single P electron. So that's going to give them a positive 3 ionic charge. If they mix with a halogen, it would look like this. So you would see something like, for instance, AlCl3. They show an increase in metallic character as you go down a group. If you take a look at group 3A, you'll see boron and then aluminum. So boron is a nonmetal. Aluminum all the way down, those are actually all considered metals, so you can see an increase in metallic character. Sorry, I said boron was a nonmetal, metalloid. Oxides will form an R2O3. This is a good indication of what you could see, like B2O3. Acidic oxide, because it's not a metal. But if you have the aluminum oxide or the gallium oxides, these are amphoteric. While they do have some metallic character, they are still kind of on this close line here. So again, you see this trend of acidic to amphoteric, and then eventually we'll have the basic come about too. Okay, so group 4 is next. You can see a change in the electron configuration again. Two special notes about the two metals at the bottom of the group, tin and lead. They either form charges of +2 or +2 or +4, but you aren't ever really sure. So these are the two that you do have to offer Roman numerals when you're doing naming, because you're never really sure whether it's going to do a +2 or a +4. When you look at calcium and silicon, those two will always covalently bond. They will not form ions because gain 4, lose 4. Which is easier here? Neither. So you're kind of between a rock and a hard place. So how about we just don't ionically bond? Let's form covalent bonds. We'll share electrons instead. Silicon and germanium are metalloids, as you can see that they are actually on the metalloid line. So anything that does actually form a bond with a halogen, and this could be a covalent bond also, is an MX4. So you could see CCl4 with 4 chlorines attached to 1 carbon, and those would be in covalent bonds. Oxides tend to have the form of MO2, and again, if you think about 4 charges and various things like that, should make some pretty good sense to you. Acidic oxides are shown there, and amphoteric oxides are shown there. Again, tin and lead, notice how close they are to the metalloid line. So they are metals, yes, but they still have some non-metallic character, which is making them more amphoteric and not completely basic. Okay, so group 5. These are going to kind of vary widely. Group 5 is kind of an interesting one. So you can see you have a few that have ionic charge of +3. You have 2 that are metalloids. And then if they would work in with a halogen to bond with that, MX3 would be the formula. Their oxides are going to vary greatly because of the differences in the metal character of each one of these. So you can kind of read this. But bismuth is definitely a metal. It's actually going to form a basic oxide. Now, you might be noticing again that I'm really throwing out all these oxide things, and this is acidic, and this is amphoteric, and this is basic. Stop worrying. You just need to have a basic understanding that if you are a metal, you're going to have a basic oxide. If you're a nonmetal, you're going to have an acidic one, and the ones in the middle, the metalloids, are going to be amphoteric. So don't stress about it. It's just more of like a trend idea, more metallic, more basic oxide. Okay, for group 6A, we have an ionic charge of -2. So these are things like oxygen, for instance. When they combine with halogens, it's MX2. So like OCl2 would be an example of a halogen compound from group 6A. We do also have oxides that can form in here, and so you can kind of take a look at this. We have some nonmetals, a metalloid, a metal, so they're going to, again, do kind of various things. Oxides at this point will start to form varied compounds. Like you can see here, an RO2, which means like, you would replace an S, say for the R, so it could be SO2, it could be SO3. we get more possibilities basically because we're now covalently bonding things together, and it's not all based on just ionic charge. So that's part of the issue that you run into here, and it becomes a little tricky, to know exactly what kind of chemical it's going to form. So some information about the oxides again, which do not worry about this overly, just understand kind of the basics. So then moving on to group 7, are halogens. These are reactive nonmetals. They are diatomic. So any of them would be considered our Hunkelbriefs. Ionic charge of -1. When they bond with other halogens, they usually do so in a 1-to-1 ratio. So again, like Cl2 or Br2. And when they form oxides, they're forming covalent compounds, and they have this really weird formula. So it could be like a Cl2O7 type of thing. Again, you don't have to memorize that. All the oxides are acidic because they all are nonmetals, and they're not very stable compounds in the first place. So again, not a huge deal. And then when you move on to group 8, finally, the noble gases. These are uncombined atoms. They do not like to form chemical compounds, relatively unreactive. You will find towards the bottom of this group, especially krypton and xenon, they will form compounds, but they're all going to be covalently bonded. The ones at the top, argon, neon, helium, do not form any compounds of any sort. So yeah, there you go. Krypton, xenon, radon are reactive. Fluorine and oxygen will combine with them, and they will exceed the octet rule, which is some stuff that we talked about. Actually, no, we will talk about later, about how these xenon and krypton specifically combining with other halogens exceed the octet rule. Whoops, darn it, did it again. Okay, so there we go. So helium and neon and argon, relatively unreactive. So again, guys, I don't want you to overly stress about memorizing what's in this presentation. What I want you to understand is that each of the groups of the periodic table have properties that are shared. Some of them, as you get especially into the P block, they have changes in metallic character, and that's going to alter some of the properties a little bit. But basically, that they all fit together in such a way as to say, like, this is where I'm supposed to live on the periodic table, and this is my family. So like I mentioned at the beginning, I would suggest maybe that you print out this presentation and just have it for reference, because it can come in handy here and there. Overwhelmingly, not a ton of stuff that you're going to use all the time, besides the basics of, like, this is what the ion charge is and things like that. So if you have questions, bring them back tomorrow and we'll talk. See you later.